If you remember, what we talked in our last lecture was about Mohr circle in 2 dimension. So there we had a stress tensor which had only 4 components: sigma 11, sigma 22, sigma 12, and sigma 21. And by symmetry, sigma 21 is equal to sigma 12, and this was the stress element which we considered for drawing Mohr circle in 2 dimension. So this is Mohr's. So we are revising it again, Mohr circle in 2D. Okay. So you remember the lower part of the Cartesian coordinate was dedicated for the anti-clockwise shear stress, and the upper was clockwise. So what will happen here, we will consider that shear stress to be positive, which will try to have rotation in this direction. So that means sigma 21, and on the opposite side we will have shear stress which will try to have a rotation of such kind, so sigma 12, right? So here we will have points, let's say here, and this point is, so this point will be sigma 12, therefore we have to take here sigma 22. So sigma 22, sigma 12 is this point, and then we have to take another point, let's say it's there, and this is sigma 11, sigma 21, right? So now we need to join these 2 points. Okay, so we will join these 2 points. Okay, and now we need to draw a circle. So we have the center point is this, and the coordinate of this center will be sigma 11 plus sigma 22 divided by 2, 0, as there is no shear stress, and this axis is sigma dash and this axis is tau dash. So this is my so I have to draw a circle which may look like this, and so not that perfect in drawing a circle, but it will somewhat look like this. Okay, so now what is the importance of Mohr circle? And in the tutorial there was a question that, why we are rotating it, why we are not happy with shear stresses. So there is no such thing that we are not happy with shear stress or we are trying to escape from there. It's just a property of this tensor. So this stress component, the state in which my stress component is now, is described by this diametrical line, right? And if you rotate this diametrical line anti-clockwise, so like this, right? So or clockwise, it doesn't matter. If you rotate this, so different points on the circumference will define different conditions of stresses. Okay, so for instance, if you reach here, so if you rotate it like this, for example, so what will happen? So if you rotate it like this, so what will happen is that your sigma 22 will increase, right? Because here this was sigma 22, and now sigma 22 has increased. Okay, so sigma 22 will increase, let's call it sigma 22 dash, and sigma 12 sigma 1 2 is this height, right? This is sigma 1 2, so sigma 1 2 has decreased. Okay, sigma 1 2 has decreased. Similarly here, sigma 1 1, so sigma 1 1 was here and now sigma 1 1 is here, so sigma 1 1 has decreased, sigma 1 1 dash, and sigma 2 1 is this, was this height, and that has also decreased, so sigma 2 1 has also decreased. So similarly, if you keep on rotating, you will reach a point here. So this is the point. So when you rotate it so that it lies on this axis, it lies here on this axis, then what happens? Then this point has reached here and here, and at these 2 points you don't have shear stress. So here shear stress is equal to 0, here also it's 0. So these 2 points define the principal stresses. So this point is sigma 1 0 and this point is sigma 2 0. Okay, and so sigma 1 and sigma 2 are the principal stresses. You know that the stress tensor now has only 4 components. So when you do sigma minus lambda I, determinant of that is equal to 0, then you will get an equation which will be quadratic in lambda, right? F of lambda square of lambda, and therefore lambda will have 2 solutions. So you will get sigma 1 and sigma 2 as principal stresses, right? And these are 2 principal stresses. So this is maximum principal stress, this is minimum principal stress, right? Now in reality what happens is that these 2 principal stresses are orthogonal to each other, so they will be 90 degrees apart. But it is the property of Mohr's circle that the angle is twice of reality. So here you can see easily that these 2 are 180 degrees apart, right? And shear stress is always the resultant between 2 principal stresses. So you have only 2 principal stresses here, so shear stress will fall between sigma 1 and sigma 2, right? And the radius of this circle is also tau max, right? And you can see that, so radius you can draw anywhere, but the direction of the shear stress where there is, so maximum shear stress will be this, and this is 90 degrees apart in this drawing, but in reality it will be between sigma 1 and sigma 2, so that will be 45 degrees. And now if you want to know that by how much degrees you have to rotate from the original state of stress so that you reach the principal stresses, you know this angle in Mohr's circle is 2 theta p, right? So in reality you want to know theta p. From this drawing you can find out that very easily without solving those equations. So you know the height of, so if you draw this right angle triangle, so this is your theta p. So this is tau max because that's the radius, and this height is sigma 1 2, right? So this height is sigma 1 2. So now you know perpendicular and hypotenuse of that right angle triangle. So sine 2 theta p, and from this you can find out theta p from the original state of stress to get the principal axis, right? So this was our Mohr circle in 2 dimension. So now let's do this in 3 dimension. So Mohr's circle in 3 dimension. So now imagine that there is a pressure vessel, okay, which looks like this. So this is actually a kind of pipe which has a thickness, some thickness, not relevant, and this is pressurized from inside, okay, and there is an axial tension. So along the axis of the cylinder, on the thickness of the pipe, you have some amount of stress. Let's call this direction x1 and this direction x2, okay. So let's say there is a stress applied here of 20 megapascal, and you have an internal pressure, so that pressure will be acting perpendicular to the wall thickness, and that internal pressure is of 50 megapascal. 50 megapascal, okay. Now we take a small stress element here, okay, in 3 dimensions. So this thickness dimension will be of the dimension of thickness, right? So we take this stress element out, and so that will look like this. We take this stress element out, okay, and so this is my x1 direction, this is my x3 direction, and this is my x2 direction, right? So along x1 direction I have a stress which is sigma 11, which is equal to 20 megapascal. I have no stress in x2 direction. I have a stress in x3 direction because of the internal pressure, and that is sigma 33 equal to 50 megapascal, okay. So I have this is my stress condition, and you see there are no shear stresses, right? So this is already the condition of principal stresses, and you know the values of principal stress. So one value of principal stress is 20 megapascal, another value is 50 megapascal, another value is 0, because I don't have any other normal stress. So the normal stress in y direction is 0. I don't have any shear stress, so all the shear stresses are 0. So these are the values of principal stresses, right? Now I want to draw the Mohr circle for this stress condition, okay. So how do I do that? So let me draw the axis again. So let me draw that again. So this is my shear axis, and this is my normal stress axis, okay. So my normal stress axis is this, and shear stress axis is here, tau dash, sigma dash, okay. Now, so let us draw the condition for, let's say, x1 x2 plane first. So x1 x2 plane, okay. What happens on x1 x2 plane? What happens here? So x1 x2 plane, what happens is I have sigma 11 of 20 megapascal. I have 0 value on x2 direction, right? And x3 direction I'm not considering because I'm taking x1 x2 plane. So what should I do now? So I have 20 megapascal of principal stress, and I have 0 value of principal stress. So one value of principal stress lies here, another value lies at 20 megapascal, okay. So I have to draw 50 also, so I can draw 10 blocks. Can I draw 20? If I can draw 20, so 2 4 6 8 10, no, 20 will go out of the screen, so I will plot 10 for 50. So 5, so 1 2 3 4, so this will be 20 megapascal, okay. This is 20 megapascal, this point here. So I need to draw a circle which looks like this, Okay, so this is the circle of x1 x2 plane. Okay, so let me write here x1 x2 plane. Now let us consider x1 x3 plane. Okay, so this plane x1 x3 plane. So in x3 I have 50, x1 I have 20. Okay, so one point is this, the principal stress value is 20, another principal stress value is 50. Okay, so this will be 50 megapascal. Okay, so now I need to draw another circle which has a center somewhere. So 3 boxes. So here this is my center, so I have to draw a circle. So this is my circle which comes from x1 x3 plane, right? Now I have to take the remaining plane, which is x2 x3. So x2 x3, what happens? x2 x3 is this plane, and on this plane in x3 direction I have stress 50 megapascal, x2 0. So I have 2 points, 50 and 0. So I have this point and I have this point, right? So let's call it A and B. So A and B are the points for x2 x3 plane. So I need to draw a circle. So this will be my center for that, and so I will be drawing a circle which will look like this. Okay, so that bigger circle is the circle for, so the bigger circle is the circle for x2 x3 plane. Now I have in this case 3 shear stresses also. So I have 3 principal stress values. One is this, another is this, and the third one is this, right? And I have 3 shear stress values. So one shear stress will lie between this and this, so that will be this. Let's call this tau 1. Then another shear stress will lie between this, and that will be the radius of this circle. Let's call that tau 2. And the third one will be radius of this circle, which will lie between this and this. Okay, and so because it will become very crowded here, so I'm drawing there, so that will be tau 3, right? But the direction you will have to calculate. You will have to understand that which shear stress will cause anti-clockwise movement and which shear stress will cause clockwise movement, and depending upon that you have to define the direction, whether it will be downside or upside. I am just drawing this to have a clear picture, right? So now, so let's see what is here. So now what is happening is we have so maximum principal stress, let's call that sigma 1 is the maximum principal stress. So that has a value of 50 megapascal. Minimum principal stress, let's call that sigma 3, value of 0 megapascal. And middle one is sigma 2, which has a value of 20 megapascal, right? So between sigma 1 and sigma 2, 50 and 20, I have a value of tau 2, right? So tau 2 is equal to sigma 1 minus sigma 2 by 2, right? Because the diameter is sigma 1 minus sigma 2, and half of that is the radius, so that is sigma 1 minus sigma 2 by 2. Similarly, tau 1, so if I take sigma 1 and sigma 3, so 50 and 0, so this is 50, this is 0. So tau 3 is equal to sigma 1 minus sigma 3 by 2. And tau 1 will be, this is sigma 2, this is sigma 3, so sigma 2 minus sigma 3 by 2, right? So these are my 3 shear stresses, and my maximum shear stress is sigma 1 minus sigma 3 by 2, that means tau 3. So you can calculate this maximum shear stress by defining an equation which can calculate shear stress and then maximizing that equation, right? You can find out principal stress by solving this equation, lambda I is equal to 0. But if you happen to know the principal stresses, then you can simply draw this Mohr circle and you can calculate the shear stress just from the drawing, and you can find out many other important things, right? If you can really draw the equation, then you know the direction of the shear stress, the angle, if you want to reach certain stress tensor value. So all those information can be obtained very easily from this diagram. Okay, so this is a very handy diagram of Mohr circle in 3D. Okay, so now we have learned how to draw Mohr circle in 3 dimension and in 2 dimension. So now we'll come to a different topic, which is the equilibrium condition for stresses. Okay, so equilibrium of stresses. So as you move on the space, then the stress values, they change, right? So if you move towards the force applied, or if you move away from the force applied, the stress values inside the material may change, may or may not change, but it depends upon how the material is deforming, right? So let us consider that the amount of stress is changing if we change along the in any direction. Okay, so we will do this for 2 dimension and we will generalize that for 3 dimension case. So let us consider a small element of stress again, right? And this is my x1 direction, this is my x2 direction, and I have so here I have sigma 1 1, right? And this dimension is very small, so let's say this dimension is delta x1, this dimension is delta x2. Okay, so I have sigma 1 1 here, and if I move by this amount of distance, then the stress has changed, and that stress has a value of, so I will write it here. So that stress has a value of sigma 1 1 plus rate of change of sigma 1 1 with respect to the direction x1 into the amount by which I have moved, that is del x1, right? Similarly, I have a shear stress which will be tau 21 or sigma 21. Okay, and with a change of x2 direction, if I go up, the shear stress changes by an amount del tau 21 by del x2 multiplied by the distance I have moved, which is x2. Okay, so in order to have equilibrium of stress, in order to have that, you know, this stress element is not moving, it is in equilibrium, I will have to have force balance in all direction, right? So let us do the force balance in x1 direction. So for that I have to do summation of forces in x1 direction equal to 0, right? So what are the forces in x1 direction? So this sigma 1 1 is applied in the negative x1 direction, so that is minus sigma 1 1. This is in positive x direction, sorry, so I have to take forces, so minus sigma 1 1 into area. What is the area of the face on which it is applied? So now I will try to draw a 3-dimension view of this so that we can understand what is the area. So let us say that the 3-dimensional thing looks like this. Okay, so in the z direction, that dimension is del x3. Okay, so that dimension is, so I will write it here. No, I will write it here, del x3. Okay, so that's the dimension, that's this dimension. So what is the area on which this sigma 11 is acting? So sigma 11 is acting on the area which is given by this dimension into this dimension. So del x2 del x3, right, plus. Now I have to take this stress which is positive, so sigma 11 plus del sigma 11 divided by del x1 into delta x1, and again same area which will be del x2 del x3. Okay, plus, sorry, minus, because this shear stress is in negative x1 direction, so minus, and now I will replace tau with sigma again, so sigma 21. Now the sigma 21 is acting on this plane, and this plane's dimensions are, so this distance is delta x3 and this distance is delta x1. So this is delta x1 delta x3 plus again sigma 21 plus rate of change of sigma 21 with respect to x2 axis multiplied by amount you have moved, which is delta x2, then del x1 delta x3. So these are the forces in x1 direction, and this should be 0, right? So simplifying this, if you open this up, so you will have minus sigma 11 delta x2 delta x3 plus sigma 11 multiplied by this, which is delta x2 delta x3 plus del sigma 11 by del x1 delta x1 delta x2 delta x3, right? Then so these are done. Then minus sigma 21 delta x1 delta x3 plus sigma 21 delta x1 delta x3 plus delta sigma 21 delta x2 into delta x2 delta x1 delta x3 equal to 0. So now you see this will cancel out, this will cancel out, and you will have only these two terms remaining. And if you look at this term and this term, this represents what? The volume of this stress element, right? So you can take that common and take it on the other side. So on the right hand side it becomes 0. So what we have remaining is delta sigma 11 by delta x1 plus del sigma 21 by del x2 equals 0, right? So our equation was del sigma 11 by del x1 plus del sigma 21 by del x2 equal to 0, and this is what we got by doing force balance in x1 direction using the two-dimensional stress element. If you have third dimension also, then we will have this equation. So we will have another term here which will be sigma 21 del x2 plus del sigma 31 del x3 equals to 0, right? So this equation appears because we are doing force balance in x1 direction. If we do force balance in x2 direction, then we will have del sigma, so we are doing it two directions, so 1 2 del x1 plus del sigma 2 2 by del x2 plus del sigma 3 2 by del x3 equals 0. Similarly, if you do force balance in x3 direction, you will have del sigma 1,3 divided by del x1 plus del sigma 2,3 del x2 plus del sigma 3,3 del x3 equals 0.